Hello guys, my name is IBM and I welcome you to my YouTube channel. And today I'm solving 9702 paper 41. This is A-level structured equations. It's actually October, November 2022. So without wasting time, I would like to take you to the question paper. So one student told me this was the hardest paper they have ever seen, so I decided to go through it slowly by slowly. So the paper is supposed to be 2 hours. I'll try my level best to keep time. I'll not read through the instructions. The paper is 100 marks. Remember, paper 4 is the most important paper. So as you'll study, if you're preparing for your May, June exams, you should spend much time practicing paper 4. So you can read through the data, you can read through the formula given, you can read through all that. I'll start with the first question. State the equation for gravitational force F between 2-point masses m1 and m2 separated by a distance r. Remember, by Newton's law of gravitation, the force is directly proportional to the product of the masses, and the force is also inversely proportional to the square of their separation. So it means the equation will be F equals to a constant, which is capital G, times m1 times m2 divided by r squared. State the meaning of any other symbols you use. So the only symbol we have added here is G. So G is the universal gravitational constant. So G is called the gravitational constant or the universal gravitational constant. A satellite is in a circular orbit of radius r around a planet of mass capital M. Show that the period t of the orbit is given by this. This is sometimes called Kepler's third law. So, because it is in a circular orbit and the force which is acting between the satellite and the planet M is the gravitational force, so we shall simply say the gravitational force provides the centripetal force or the centripetal acceleration. Because the question says you should also explain your working, so we shall simply say the gravitational force provides the centripetal force, or it provides the centripetal acceleration. Remember, the gravitational force is constant and is always perpendicular to the direction of motion of the particle. Therefore, it does not change the speed, but instead it changes the direction. Therefore, it just provides the centripetal acceleration. So centripetal force is gravitational force. We have already written an expression for the gravitational force in part A. So I'll simply say G capital M. I'll use small m for the satellite. Divide by r squared for the radius of orbit. This should be called the centripetal force. The centripetal force is given by mv squared divided by r. So one r has cancelled out with the square. And I want you to also remember that v is equal to omega times r, where omega is 2 pi divided by t. So v is 2 pi over t, then times r. So I'm going to again replace this. So I have g m small, of course, small m has cancelled. So over r is equal to v squared. Where there is v squared, I'll put 2 pi times r over t, but this should be squared. So when I simplify this, I have that capital G, capital M is going to be 4 pi r cubed divided by t squared. This r on the left hand side goes to the other side. So if I cross multiply this, I have that t squared is going to be equal to 4 pi, or this is 4 pi squared. It's 4 pi squared divided by G capital M, then times r cubed. So it means this quantity here is going to be a constant. So we shall say t squared is equal to k times r cubed, where K is going to be equal to 4 pi squared divided by G times capital M. As simple as that. Then a satellite is in a circular orbit around the Earth with a period of 24 hours. The mass of the Earth is 6.0 times 10 to the power of 24 kilograms. Calculate the radius of orbit. So we have already said T squared is equal to 4 pi squared over G times M times R cubed. So I'll just make R cubed the subject, or I'll find R being equal to GM T squared divided by 4 pi squared, and this one will be to the power of 1 over 3, or the cube root. So when I try to substitute, G is 6.67 times 10 to the power of minus 11. The mass is 6.0 times 10 to the power of 24. The period is 24 hours, so it is going to be 24 times 3,600 to change it to seconds. So this is going to be 24 times 3,600, and this is squared. Then now I'll divide this by 4 pi squared. And of course, this should be to the cube root because r was raised to power 3. So I'll check with my calculator. I'll start with the simplest part. I'll start with 24 times 3,600. But this is raised to the power of 3. Then I multiply this by 6. Sorry, I raise it to power 3. I'll have to repeat this. 24 times 3,600. And this is squared. Then times 6 exponent 24, then times 6.67 exponent minus 11. Then I divide this by 4 pi squared. Then I'm going to find the cube root. So I'll find the cube root. Let me just say shift cube root of the answer. So this is giving me 4.23. 4.23 times 10 to the power of, this is 367 power 7. So the radius is going to be 4.23 times 10 to the power of 7 meters. Okay. Then state two other conditions that must be met for the orbit to be geostationary. Remember, for a geostationary satellite or for a geostationary orbit, they are just two, because geo means with reference to the Earth, and stationary means when you view the orbit from the Earth, it appears to be stationary. So the period is the same as the period of the Earth, which is 24 hours. Then it is also from west to east, just like the rotation of the Earth. And also it is above the equator, so we say it is in equatorial orbit. These are the three conditions. The first one has been mentioned, so we have to state the two remaining ones. So we can say direction must be from west to east. Direction must be from west to east. That's number one. Then the second one, it is in equatorial orbit. Orbit must be just above the equator, so I'll say the orbit must be just above the equator. So the orbit must be just above the equator, that is for a geostationary orbit. If it was mattostationary, that is from Mars, of course the direction must be the same as that of Mars around the Sun, and it should be just above the equator of the Sun, of Mars, if Mars has equator anyway. Okay, so that was question number one, gravitational fields. Question number two is, I think, heat, temperature, and ideal gases. The figure shows a laboratory thermometer that is calibrated to measure temperature in degrees Celsius. It is in degrees Celsius. The thermometer makes use of the fact that the density of mercury varies with the temperature. Yeah, of course, as temperature increases, the length of the liquid column increases to indicate an increase in temperature. State two other physical properties of materials apart from density of a liquid that can be used for measuring temperature. Those are the physical properties of physical properties that you must have mentioned in a unit called temperature and ideal gases, thermal properties. So you must have mentioned the resistance of a metal wire changes as temperature changes. Resistance of a metal wire. If a metal wire resistance is directly proportional to temperature, if it is a thermistor, resistance is inversely proportional to temperature. That's number one. Number two, you can talk about the volume of a gas at constant pressure. Volume of a gas at constant pressure. Remember, PV is equal to nRT. If pressure is constant, then volume is directly proportional to temperature. Then the third one, you can talk about the EMF of a thermocouple. The EMF of a thermocouple. So this is one word, thermocouple. The EMF of a thermocouple. I think this is all, thermocouple. So if you remember from IGCSE concepts, you looked at a thermocouple. So the PD across two junctions of a thermocouple is directly proportional to the temperature. You can also talk about the color of an electrically heated wire. Different colors can be seen if the temperature is in a certain range. So the temperature is directly proportional to the color of an object which has been electrically heated, and so on and so forth. So you needed to state only two. The thermometer is initially at 23 degrees Celsius, as shown in the figure. It is used to measure the temperature of an insulated beaker of water that is at 37.4 degrees Celsius. The bulb of the thermometer is inserted into the water, and the water is stirred until the reading on the thermometer becomes steady. The mass of the water is 18.7. This is mass of water in the beaker. The mass of mercury in the thermometer is 6.94 grams. Specific heat capacity of water is 4.1 joules per gram per Kelvin. Specific capacity of mercury is 0.140 joules per gram per Kelvin. Because the masses are in grams and the heat capacities are in joules per gram, I will not convert the units. The glass of the thermometer and the beaker containing the water can be considered to have negligible heat capacities. Calculate to three significant figures the final steady temperature indicated by the thermometer in the water. So we know that the energy Q is equal to mc times change in temperature delta T. So we assume that the heat which is lost by the water should go into raising the temperature of the mercury. So I will say heat lost by the water, or the heat which leaves the water, because the water was the one which was at a higher temperature of 37.4 degrees Celsius. The heat lost by the water should be equal to the heat gained by the mercury. So remember, at equilibrium, the water and the mercury will have now to reach now be at the same temperature. So the heat lost by the water is going to be the mass of the water, specific capacity of the water, times change in the temperature of the water. And then the heat gained by the mercury should be the mass of the mercury specific capacity of the mercury times the change in the temperature of the mercury. So the heat lost by the water is going to be the mass of the water, which is 18.7. This is in grams. Specific capacity is 4.18, which is joules per gram per Kelvin. It is joules divided by grams per Kelvin. Then times the change in the temperature. So the temperature falls from 37.4 to the final temperature, which I'm going to call T. This should be equal to the mass of the mercury, which is 6.94. This is in grams. Specific capacity is 0.140 joules divided by grams Kelvin. Then the temperature, of course, for the mercury, the temperature rises. So it means the final temperature of mercury is higher than its initial temperature. So we shall say the final temperature minus the initial temperature of mercury, which was 23.0. Okay, so I'm just going to simplify this. Of course, grams cancels out. So if I try to solve this, let me try to simplify this. I have 18.7 times 4.18. So I'm going to have a minus 78.166T. I just want to multiply this by 37.4. So this side I have 2923 point. I want to use the whole values. 0.4084 minus that. I've opened that bracket. On the other side, I have 6.94 times 0.14. So this is going to be 0.9716. That is T minus. I will multiply that by 23. So times 23. So this is 22.3468. 22.3468. So I try to open the brackets at once. So I'm going to collect like terms. So when I collect like terms, I'll add this to the other one. So I have that one plus 2923.4084. So on one side, I'm going to have 2945.7552 should be equal to, on the other side, I'm taking 78 to the right hand side. So it will also be plus. So I'll say 0.9716 plus 78.166. So this is 79.1376. 79.1376. This is T. So I'm just going to divide both sides. So I'll have 2945.7552. I divide this by the answer, which is going to give me 37.2. So T is equal to 37.2. So I'll write here 37.2 degrees Celsius. Because they say to three significant figures, the answer is 37.2 degrees Celsius. Now the algebra which comes after here, it depends on, it doesn't carry any mark because the marks are here, and being able to discover that statement, substitution, then the final answer. The algebra will not carry any serious mark. So whatever shortcut you use is fine. So just one change that could be made to the design of the thermometer that would enable it to give a more accurate measurement of temperature. We want to design or to improve, we want to change the design of the thermometer so that it gives a more accurate temperature. So if it is to give a more accurate temperature, we should make sure that we use a liquid which expands very fast as temperature increases. Therefore, we could use a liquid which has a lower specific capacity, and if a liquid has a lower specific capacity, means a small change in the temperature a small change in the surrounding will cause a bigger change in temperature, which can easily be seen in the thermometer. That's number one. Number two, we would also make this. We could also use a smaller mass of mercury, so that because the smaller mass will easily gain heat, so we could also use a smaller mass, because note that the change in temperature, we are using Q is equal to mc delta T. So we want to cause to produce a more accurate measurement. It should give a greater change in what? In temperature. And note that change in temperature is inversely proportional to C, and change in temperature is inversely proportional to the mass. So one, we should use a liquid with a lower specific capacity. Use a liquid with a lower specific heat capacity. Why? Because a smaller heat capacity will give a bigger change in temperature. Remember, whenever the measured value is bigger, it means it's going to be more accurate and even more precise. It has a smaller percentage uncertainty. Then the second one, because change in temperature is inversely proportional to mass, so we can use a smaller mass of mercury. Use a smaller mass. Use a smaller mass of mercury. So n of those two, because they wanted only one. Explain why the thermometer in the figure does not provide a direct measurement of the thermodynamic temperature. So this one does not provide a direct measurement of the thermodynamic temperature. First of all, the Celsius scale, it's 0 degrees Celsius is not the same as absolute zero. That is in the first place. And of course, the temperature on this scale depends on the properties of a real substance. Yet the temperature on the thermodynamic scale does not depend on the properties of a real substance. So I'll simply say the temperature from thermometer, the one which we have there, depends on the properties of a real substance. Which is not the case with the absolute scale. And also 0 degrees Celsius on the thermometer is not absolute zero. On 0 degrees Celsius on the thermometer, on this thermometer that we have, is not the same as absolute zero on the thermodynamic scale. In fact, absolute zero on the thermodynamic scale is negative 273 degrees Celsius. In the thermometer, the thermodynamic temperature T may be determined by the behavior of a type of substance for which T is proportional to the product of pressure and volume. T is proportional to the product of pressure and volume. In other words, PV is equal to a constant times T. State the name of this type of substance. Of course, this is only for an ideal gas. This is an ideal gas. Okay, so the gas there is ideal gas. So that is the end of that topic. I think the next is simple harmonic motion. An object is suspended from a spring that is attached to a fixed point as shown. Okay, so this is the equilibrium position. The oscillations are vertically up and down. The object oscillates vertically with a simple harmonic motion about its equilibrium position. State the defining equation for simple harmonic motion. Identify the meaning of each of the symbols used to represent physical quantity. So we know that for simple harmonic motion, this equation is given in the list of constant, list of formula. A is equal to negative omega squared x. I think it is sometimes given in the list of formula unless it was not given in this paper. So this equation is given in the list of formula. A is equal to negative omega squared x. You can always check. So we just write it here. A equals to negative omega squared x, where A is the acceleration, then x is the displacement, of course. Then, by the way, x is displacement from equilibrium position. It is measured from equilibrium. Displacement from equilibrium position. And omega is, of course, the angular frequency. People call this W, but this is omega, which is angular frequency. Okay. The variation with the displacement x from the equilibrium position of the velocity v of the object is shown in the figure. So this is a graph of velocity against displacement. At this point, you should also be recalling that v is equal to omega square root of x naught squared minus x squared. And this equation is also given in the list of formula. Then the variation with the x of the potential energy EP of the oscillations of the object is also shown in the figure. Use figure 3.2 and figure 3.3 to determine the amplitude. Use figure 3.2 and figure 3.3 to determine the amplitude. So use figure 3.2 and figure 3.3 to determine the amplitude x naught of the oscillation. So I'll first go back to figure 3.2 to determine the amplitude. Remember, if I use v equals to omega square root of x naught squared minus x squared, when x equals to 0, what is v? V is maximum. When x equals to 0, v is maximum until 0.2. V is 0.2. So it means I will say 0. No, this will not save my time. I want to use v equals to 0. When v equals to 0, it is because x equals to x naught. So when v equals to 0, then x is equal to x naught. I'll check from the graph. When v equals to 0, x is equal to x naught. So the displacement, v is equal to 0 along the x-axis. So this is the point here, or this side, this point here. So it means the displacement is going to be equal to 0.12. The units given there are in meters, so this is going to be 0.12 meters. Then show that the angular frequency of the oscillation is 1.7. Remember, I'm using v equals to omega square root of x naught squared minus x squared. And we have already seen that for x equals to 0, then v equals 2 from the graph. For x equals to 0, v is equal to 0.2 meters per second. So v is equal to 0.2 meters per second. We already know x naught, so I'll just substitute. So I'll say 0.2 equals to omega square root of x naught, which is 0.12 squared, minus x, which is 0 squared. So when I make omega the subject, omega is going to be equal to 0.2 divided by the square root of 0.12 squared, which is the same as 0.2 divided by 0.12. You could use any other formula to find, you could even use the one of energy to find omega if possible. So I have 0.2 divided by 0.12, which is 1.66 recurring. So this is approximately a 1.7 radians per second. Then determine the mass m of the object. So there's no way I'll use the first equation of v is equal to omega x root of x naught squared minus x. I must use the one which has mass, which is the one of energy. So we know that the maximum potential energy is equal to a half m omega squared x naught squared. I'm using maximum energy. Of course, when kinetic energy is 0, when ek equals to 0, then E potential is equal to maximum potential energy, which is a half m omega squared x naught squared. So I'm just going to make a substitution. From the second graph, maximum energy is 0.05. So I'll simply say 0.050 should be equal to a half times the mass times omega squared, which has been quoted as 1.7 squared. Then we have already seen x naught to be 0.12 squared. So I'll just press my calculator by making the subject. I have 0.05 times 2. Then I'll divide this by 1.7 squared times 0.12 squared. So this is giving me 2.40. 0.05 times 2 divided by 1.7 squared divided by 0.12 squared. So it is giving me m as 2.4 kilograms. So m is 2.4 kilograms. Let me try to use a more exact value. So I'll say 0, method 2 is substitution. I'll substitute in 0.050 equaling to a half times m times, instead of using 1.7, I'll use 0.2 over, because omega squared, omega is 0.2. Did I find the square root here? Okay. Yeah, omega is 0.2 divided by 0.12. And remember, this was squared. then times 0.12 squared. I will try to use the more exact value, and I see, because the value may vary between 2.4, 2.5. So I have 0.05 times 2 divided by 0.12 squared. Then I will divide this by 0.2 divided by 0.12, but the whole of this is squared. What have I done? Okay, let me repeat this. 0.05 times 2. Then divide by 0.12 squared. Then I'm going to divide this by open brackets. 0.2 divided by 0.12, close this bracket, but this is squared, which gives me 2.5. So m is most likely going to be 2.5, depending on how you round off, or it is going to be 2.4, depending on if you use if you use a rounded value of omega, you'll get 2.4. If you use an exact value of omega, you'll get 2.5 kilograms. So the examiner will decide the tolerance, but most likely both answers will be credited. Then the oscillations of the object are now lightly damped. We know lightly damped means the amplitude gradually decreases but the oscillations continue over a certain period of time. So damping simply means loss in energy of oscillation of a system due to dissipative or resistive forces. So loss of total energy. Loss of total energy of oscillation of a system due to dissipative, you can call them resistive, I think resistive is single S, due to resistive forces. That's what we call damping. You should be referring to loss of energy due to dissipative or resistive forces, that is damping. Assume that the damping does not change the angular frequency, so omega is going to be the same. On the figure, sketch the variation with x. We are sketching on figure 3.2. The variation with x of v when the amplitude of the oscillations is 0. Sketch the variation of x with x of v when the amplitude of the oscillations is 0.060 meters. So first of all, we know that maximum velocity is going to be maximum. Velocity is maximum when the displacement is 0. So let's first find the maximum velocity. So using v equals to omega square root of x naught squared minus x squared. So velocity is maximum. Maximum velocity is equal to omega, which is going to be the omega. Let's just use 1.7 times, but I always want to use the previous value. So let me try to use the previous value, which was 0.2 over 0.12. That was omega times the square root of x naught. Because the amplitude has changed to 0.06, so x naught is going to be 0.06 squared minus, this is going to be 0. When the velocity is maximum, v is maximum when displacement is 0. So it means the maximum velocity is going to be, I'll just press my calculator, to be 0.2 over 0.12 times 0.06 because of the square. So I have 0.2 times 0.06 divided by 0.12, which gives me 0.1. So this is going to be 0.10 meters per second. So it means when x equals to 0, V is going, or V maximum is going to be plus or minus 0.10 meters per second. It is going to be when x is 0, V will be either plus 0.1 because it is always in both directions, or it is minus 0.1. Then how about when x is equal to maximum? When x equals to x naught, which is 0.060. Of course, when I substitute in the equation, V is equal to, V is going to be the omega into into the square root of 0.06 squared minus 0.06 squared. So that means when x equals to either positive or negative 0.060, V is automatically going to be 0. So I have 4 points. Here I have 0 plus 0.1. I also have 0 minus 0.1. Then here I also have 2 points. I have 0.06 against 0. This is positive. I have negative 0.06 against 0. Okay, so I'm going to just sketch those points on the graph. So on this graph, I must look for when V is 0 on the x-axis, when velocity is 0, or velocity is 0 when x equals to 0.6, 0.06, or 1, 2, 3, 4, 5. I think this is 0.06. So the graph will cross that point, and it will also cross this point, which is negative 0.06. Here velocity is 0. Then when the displacement was 0, velocity was maximum, and it was plus or minus 0.1. So it will cross this point here and this point here. So I'm going to draw a curve, an oval shape inside here. Okay, so you can draw a better shape than mine. You could use really want to draw a better shape, because normally students try to draw things which are very funny in an exam. Okay, so you can draw something better than mine. At least I've tried to draw that. It should touch this point here, that point, and this point here. So that will be the graph. It's an oval shape inside. Next is question 4, which is electric fields. State what is indicated by the direction of an electric field line. Of course, for electric fields, you should always be referring to a positive charge. So the direction of the electric field line, this one shows, or it indicates the direction of force on a positive charge. It indicates direction of force on a positive charge. That's what the direction of the electric field line indicates. If it is a magnetic field, it will indicate the direction of the force on the north pole. If it is a gravitational field, it indicates the direction of force on a mass. The figure shows a pair of parallel metal plates with a potential difference of 2,400 volts. The plates are separated by a distance of 4.6 centimeters. The plates are in a vacuum. So if they're in a vacuum, we don't expect anything around the plates or inside the plates. On the figure, draw 5 lines to represent the electric field in the region between the plates. So we want to draw 5 lines. Remember, this is going to be a uniform field because the plates are parallel. And because it's a uniform field, the field lines are going to be evenly spaced or equally spaced. So I'm going to draw field lines which are equally spaced. So I'm going to try my level best to ensure that they are almost equally spaced. Okay, so I tried my level best. You can make sure that they are equally spaced. There are 5. Then field lines originate from high potential to low potential. So these are going to point vertically downwards. Okay, so these free marks are just for nothing. So that is all. Calculate the strength of the electric field between the plates. So strength is E. And remember, by definition, E is either force per unit charge or it is going to be V divided by D. Since they gave us V and we know the separation, then it is going to be 2,400 minus 0, of course, divided by the separation, which is 4.6 centimeters. So it is going to be 4.6 times 10 to the power of minus 2. So 2,400 divided by 4.6 exponent minus 2. So I'm getting 5.2 times 10 to the power of 4. So this is 5.2 times 10 to the power of 4 newtons per coulomb, or it could be volts per meter. A moving proton enters the region between the plates from the left, as shown in the figure. So it is a proton, which means it is positively charged. So as soon as it enters the field here, the force on it is in the direction of the field. It is going to be downwards. So the path should be downwards. The proton is deflected by the electric field. On the figure, draw a line to show the path of the proton as it moves through and out of the region of the electric field. So of course, I'll have to prolong this line first of all as a horizontal line before it reaches the electric field. But when it enters the electric field, now the force acts on it. So I am going to draw a curve because they said through and out of the region. So of course, out of the region it enters a vacuum again. That means out of the region again it experiences no deflection. I want to draw something better. Okay, so you can draw something better. Of course, when you reach the exit to the plates, then you draw what? A tangent. It should be a tangent. This part here should be a tangent to the curve. This is not a tangent. You should draw something which is better, a nice smooth curve. And at the point where it emerges, you should draw a tangent, which is a straight line. This part here should be straight. That part there should be a straight line because here it is entering in a what? In a vacuum again, where the electric field is not acting. So this part should be a tangent. This is going to be a smooth curve. The reason as to why it is downwards is because it's a proton, so it experiences a force towards or in the direction of the electric field. So it is going to move downwards. The helium nucleus now enters the region of the electric field. It is a helium. Of course, it has a mass of 4U. The proton, remember, had a mass of 1U. The proton is P11, mass is 1U. This one has a charge of twice E, the other one has a charge of plus E. Okay. State and explain how the final speed of the helium nucleus compares with the final speed of the proton after leaving the region of the electric field. So we're now talking about speed. If we to talk about speed, we must talk about the force. Therefore, we should talk about the acceleration. Remember, the electric field strength remains constant. So we know that E is equal to F per unit charge, which is equal to the mass times the acceleration over the charge Q. So it means the acceleration is going to be Q times E divided by M. So for the proton, acceleration of a proton is going to be, the charge is E. I'll just say E over the mass, which is 1U times E. Then the acceleration of the helium particle, which is the alpha particle, is going to be the charge, which is twice E, over the mass, which is 4U, then times E. So I want you to notice that this is the same as a half E times capital E over U, which means the acceleration of the alpha particle is equal to a half the acceleration of the proton. Now that the acceleration of the proton is twice the acceleration of the alpha particle. And remember, the acceleration, of course, affects the speed. So it means it implies that the final speed of the helium is going to be lower. Even if they start with the same initial speed, it means the final speed of the helium is going to be lower than the final speed of the proton, because the speed depends on the acceleration. And remember, the acceleration is vertically downwards. It is not in the horizontal. So to start, I'll start with talking about the charge and the mass. So I'll say the charge of helium is twice that of proton, but its mass is 4 times the mass of a proton. And so the acceleration, which is in the vertical, so acceleration perpendicular to the plates is smaller for helium. So the acceleration either parallel to the field or perpendicular to the plates, the acceleration perpendicular to the plates is smaller for helium. The acceleration is smaller, so even if they enter the field with the same speed, initial speed, it means, so the acceleration perpendicular to the plates is smaller for helium, and the velocity perpendicular to the plates is going to be smaller. And so velocity of helium perpendicular to the plates is small, because of course the body access the direction of the velocity. So, but of course there's another velocity which is parallel to the plates, which remains constant because there's no resultant force in the horizontal. So the velocity of helium perpendicular to the plates is small, and yet velocity parallel to the plates is the same. So it means, remember the final speed, they have a speed in the horizontal and speed in the vertical. The speed in the horizontal remains constant because there is no force acting horizontally, but the speed in the vertical must increase because there is a force acting in the vertical. But because the acceleration of helium is smaller, it means its velocity in the vertical is also going to be small. So the resultant is the Pythagoras theorem gives us the resultant between these two velocities. But we are saying the velocity parallel to the plates is the same for both. So hence the final speed of helium is lower. So the final speed of helium is going to be lower, because if I find the resultant of the two velocities, since this is the same for both, because there is no force in the horizontal, but the one in the vertical is changing because the one in the vertical is depending on the acceleration, which acceleration is depending on the resultant force, which force is depending on the charge and the mass, then it means the final speed of helium is going to be lower. I think that was electric fields. Next is capacitance. A capacitor of capacitance 740 microfarads is connected to a battery of EMF 24 volts in the circuit of figure 5.1. So this is what we have. The two-way switch S is initially at position X. So in position X, the capacitor of 740 microfarads is charged. These wires are placed, P and Q are identical long straight wires. Each wire of resistance are 5.6 kilo ohms. These wires are placed near to and parallel to each other. Wire Q is connected to a voltmeter. So it means if there's a change in magnetic field around wire Q, the voltmeter should give a reading to indicate an induced EMF in the wire. At T equals 0, switch S is moved to position Y. Of course, when we move the switch to position Y, it means the capacitor must discharge across P. But obviously, it discharges across P. Basically, the PD across P is going to start decreasing or increasing during discharge, which will cause a changing magnetic field, which is most likely going to cause an induced EMF around wire Q. At time t equals 2, so the switch is moved to position Y so that the capacitor discharges through wire P, capturing the charge Q naught. Of course, we know that charge is equal to C times V. So the charge Q naught is going to be the initial capacitance C naught times V naught. Of course, C naught is 470 microfarads. The one the answer in column, so I would say this is 470 times 10 to the power of minus 6, then times V naught. Of course, when a capacitor is fully charged, the PD across its plates is the EMF of the power supply, which was 24. So I'll just simply say 470 exponent minus 6 times 24. So this is giving 0.0113. 0.0113. Then calculate I naught, the current I naught in the wire P at time t equals to 0. So of course the current is going to be equal to V over R. We have not, at time t equals 0, this charge has not yet started. Oh, this charge has just started. That means the PD across P is going to, because the PD across this one is 24, it means the PD across the wire here is also going to be 24 volts at t equals to 0 when this charge just starts. Of course, as the PD across the capacitor reduces as it discharges, the PD across P also reduces. So at t equals to 0, V is going to be equal to 24 volts across P because the wire is in parallel with the capacitor. So it means the current I is going to be equal to 24 divided by the resistance C of the wire, which was given as 5.6 kilo ohms. Okay, so 24 divided by 5.6 exponent 3. So this is going to give us 0.0. I'll write three significant figures. So I'll write 4.29 times 10 to the power of. It's always bad to write less than two significant figures, so I prefer to write 3. But you can always write 2, unless asked to write more. So that is 4.2 times 10 to the power of 1, 2, 3, power minus 3. Then I'll calculate the time constant tau of the discharge. Of course, we know time constant is the product of the resistance times the capacitance. So the resistance is 5.6 times 10 to the power of 3. Then the capacitance is 470 microfarads. So it's 470 times 10 to the power of minus 6. So I'll check my calculator. 5.6 exponent 3 times 470 exponent minus 6. So this is 2.63. Okay. Then on the figure, sketch a line to show the variation with the t of the time I in a wire P as the capacitor discharges. Of course, we saw in your class, you must have seen that the discharge is exponential. In other words, I after time t is equal to I naught e power negative t over RC. Or you must have seen I is equal to I naught exponent negative t over RC, where RC is the time constant. So it means at t equals to 0, I should be equal to I naught. So our graph starts from here. And then let's see what happens when t tends to infinity. As at t, or as t tends to infinity, of course it means when you substitute infinity there, you notice that I will be tending to, when I put infinity there, let me check, a bigger value. As t tends to infinity, e power negative a big value. I will just check with a big value for those who are not mathematicians. As t tends to infinity, of course, I know I tends to 0, but some people may want to know how. If t is infinity, negative infinity over RC is approximately infinity. So e power a negative bigger value tends to 0. If e power 0 is 1, then e power negative bigger value automatically tends to 0. So I'll not even waste time checking this. So this is going to be an exponential curve, so which tends towards the x-axis, but of course it should not touch the x-axis. So this is going to be a curve like that. It starts from I naught, remember? It starts from I naught. Then explain why there is an induced EMF across Q during the discharge of the capacitor. Of course, that is obvious. When there is discharge, the PD across P changes, the current through P changes, and if the current through P changes, it gives rise to a changing magnetic field around P. A changing magnetic field around P cuts or is being cut by the wire Q, which by Faraday's law an EMF is going to be induced. And if an EMF is induced, it must be registered by the voltmeter. So I would simply say the current in wire P gives rise to a magnetic field. The current in wire P gives rise to a magnetic field around P. And as the current in P changes, because we have seen the graph above, the current is changing. As the current in P changes, Of course, it means the magnetic field is going to be changing. So as the current in P changes, wire Q cuts are changing magnetic flux of wire P. So because the current in P changes, it means the magnetic field around it is changing, and the magnetic field, remember, is being cut by a wire Q because it's very close. Then by Faraday's law, the cutting magnetic flux causes induced EMF across Q. Cutting magnetic flux causes induced EMF across Q. As simple as that. First of all, I've mentioned that the current in wire P is creating a magnetic field around the wire. But of course, from the above graph, the current is changing, which means there's a changing magnetic field around around P, which is linked to wire Q, because wire Q is in that magnetic field. And by Faraday's law, the cutting magnetic flux um, around wire Q, or the cutting of magnetic flux around wire Q, around wire P by wire Q, induces an EMF across wire Q. On the figure, sketch the line to suggest variation with the T of the voltmeter reading V. So of course we know that V is going to be equal to V naught e power negative T over RC. So it means, it also means V is actually going to be just directly proportional to, V is going to be just directly proportional to the current. So it means when T equals to 0, before this charge, when T equals to 0, V, the induced EMF across, or the induced EMF across, or the reading of the voltmeter is going to give us a value V naught. But of course, as T changes, V is equal to V naught here at T equals to 0. But then as time goes on, as T tends to infinity, it also means V is going to be tending to 0. So the graph will start from a certain point there, and it will tend towards the x-axis with a negative gradient, exponential. As simple as that. Then as this is still magnetic fields, I think the figure shows a thin slice of conducting material used in a hole probe. Current I passes through the slice in the direction shown. Okay. The slice is placed in a uniform magnetic field of flux density B so that two of its faces are perpendicular to the magnetic field. A steady hole voltage VH is developed between PQXW. So it is the hole voltage is between this point here and this point here. Okay. Use the letters in the figure to identify the faces that are perpendicular to the magnetic field. Okay. So if the hole voltage is between PQXW, it means the force due to the electric field is either in that direction or in that direction, depending on the nature of the particle. And if the current is in this direction, then the magnetic field must be perpendicular, remember? So the magnetic field must be vertically downward. So it is either perpendicular to PQRSP or it is perpendicular to WXYZW. So Identify the faces that are perpendicular to the magnetic field. So it is P, Q, R, S, the top face, P, Q, R, S, and the one at the bottom, which is W, X, Y, Z. Explain why the steady Hall voltage VH is developed. Steady meaning constant is developed between faces P, Q, X, W, and S, R, Y, Z. So number one, the force due to the magnetic field is going to be perpendicular, or the force on the charge carriers is perpendicular to the magnetic field, and also it is going to be perpendicular to the current, that is by Fleming's left-hand rule. So as charge carriers are deflected onto either P, Q, X, W, or S, R, Y, Z, an electric field is being set up, so a Hall voltage is set up. But then this Hall voltage becomes constant when the force, or the electric force, and the magnetic force on the charge carriers are equal and opposite. So I'll simply say the force on charge carriers is perpendicular to both the magnetic field and the electric field. The force on charge carriers is perpendicular to both the magnetic field and the electric field. So if the force is perpendicular to both the magnetic field and the electric field, it means these forces are going to be in the opposite directions. So as charge carriers are deflected to one side, as charge carriers are deflected to one side, an electric field what did I say? Force on charge carriers is perpendicular to both the magnetic field and the current, not electric field, because here the electric field has not yet been generated. The force is perpendicular to the magnetic field and the current. That is according to Fleming's left-hand rule. And as charge carriers are deflected to one side, an electric field is set up. So a Hall voltage. Is set up. So this Hall voltage, or the Hall voltage, becomes steady or becomes constant when the electric and magnetic forces on the charge carriers are equal and opposite. Okay, so the whole voltage becomes steady or becomes constant when the electric and magnetic forces on charge carriers are equal and opposite. So at that point, then it means it cannot increase any further. No more electric field is generated. So the whole voltage becomes constant. The magnitude Vh is given by the equation Vh is equal to Bi over NTQ. What do these letters stand for? So to start with, N, I think N is the number density of charge carriers. Number density of charge carriers. Number of free electrons per unit volume, that is number density of charge carriers. Then T, I think T stands for the thickness. They said you may refer to the letters in the figure. So D is distance, T is going to be distance. I'll just choose one pair. So this is T here, either SZ, or it can be PW, it can be QX, or it can be RY. So that is T, or thickness. T is distance PW, or you could say distance SZ, or I say distance, I think it is QX, or I say distance RY. Of course, you don't write all those. Let me check. RY, QX, PW, SZ. So T is thickness, which can be any of those distances. Then what is Q? Of course, Q is the charge on each charge carrier. Charge on each charge carrier. Suggest with the reference to the equation why the slice of the material used in a hollow probe is thin. So this takes us back to the equation. VH is inversely proportional to T, where T is the thickness. So VH is inversely proportional to T. So it means T needs to be small enough for VH to be large enough. So T needs to be small for VH to be large enough to measure. T needs to be small for VH to be large enough to measure. If T is big, VH is small, then measurement of G will give a large percentage uncertainty. But if T is small and VH is going to be V is going to be large enough to measure, then the percentage uncertainty in VH will be smaller. Okay, next is alternating current, I think. A sinusoid alternating voltage has a root mean square potential difference of 4.2 volts and a frequency of 50 kilohertz. The alternating voltage is applied across a resistor of resistance 760 ohms. By considering the peak voltage, that is V naught, so that the maximum power dissipated by the resistor is 46 milliwatts. So we want maximum power. So remember, to find maximum power, if it is a DC value, power is equal to V squared over R. That is for DC values. Then for for alternating values, then it means maximum power is going to be V naught squared divided by R. But remember, V root mean square value is equal to V naught divided by root of 2. So it means peak is going to be root mean square value By considering the peak V naught, the peak voltage V naught, show that the maximum power dissipated by the resistor is 46 watts. So they gave us the root mean square as 4.2. So this will be 4.2 times root of 2. That is going to be V naught. So it means the maximum power is going to be 4.2 root of 2. This is squared, remember, divided by the resistance, which is 760. So just check my calculator. 4.2 root of 2, but this is squared, divided by 760. So this is 0.046. 0.046 watts. I think when I divide this by 1,000, 0.046, divide this by 1,000 for milli. Let me see, divide by 1,000. No, it is actually times, not to bring in milli, I divide by the value for milli, which is 10 to the power of minus 3. Okay, so this was wrong. 0.046 divided by 1 exponent minus 3. I think that is 46 milliwatts. On the figure, draw a smooth curve to show how the power P dissipated in the resistor varies with the time t between t equals to 0 and t equals to 40 microseconds. Assume that P is equal to 0 when t equals to 0. So the graph starts from here. And remember the equation of power. Power at any given time is going to be power P naught sine of omega times t. Actually, it is sine squared omega times t. That is power at any given time. Then let's first find they told us between t equals to 0 and t equals to 40 seconds. Let's first find the period. They gave us frequency and period is equal to 1 over f, which is going to be 1 over, the frequency was 50. So 1 over 50 times 10 to the power of 3, which is going to be 1 over 50 times 10 to the power of negative 3. I just want to divide 1 divided by 50. That is 0.02 times 10 to the power of minus 3. So here they gave us this is in microseconds. So I want this is in seconds. I want to change this to micro and I see. So this will be 0.02 times 10 to the power of minus 3 divided by 10 to the power of minus 6. So times 1 exponent minus 3 divided by 1 exponent minus 6. So this is 20 microseconds. So whenever it is 20, that is one complete cycle. 10, that is half a cycle. Then 5 is a quarter cycle. This is 5, 15, 15, that is 25, and then 35, and so on and so forth. So we know that the maximum power is 46. So I will look for 46. On the vertical, the scale is 25 divided by 10. Each small box is 2.5. So I want to plot 46. Let me look for 46. 46 divided by 2.5. So I'll count 18.4 boxes. 1, 2, 3, 4, 5, 6, 7, 8. So it's approximately here, approximately 18.5, 18 and a half boxes. So if at t equals to 0, the power is 0, then at t equals to a quarter of a period, the power should be going to maximum. If you want, you can make substitutions here. When t is a quarter period, I'll just do a quarter period only for just for the sake. So at t equals to 0, the power was 0. That means we use a sine graph. So at t equals to a quarter of a period, then power is going to be equal to P naught sine squared of, remember omega is 2 pi over t, then times a quarter of a period. So it means P is going to be P naught sine squared of, this is going to be pi divided by 2. And of course, we all know that sine of 90 is 0. So it means we know that sine of 90 is it 1? Let me check. Pi over 2 is 90. Sine of 90 is 1. When you square it is 1. So P is equal to P naught, which is maximum. So at a quarter period, we have maximum power. Of course, at a half, it will go back to 0. At 15, it will go back to maximum. No, it is here. 18 points, so it is here. So at 15, so the graph will go like this. Maximum at 5, it goes back to 0. Then at 15, it goes back to maximum again. Then at 20, of course, it goes to 0. Then at 15, it goes back, at 25, it goes back to maximum again. And at 30, it goes back to 0. At 35, it goes back to maximum. Then at 40, it goes back to 0. Okay, so that would be the graph. If you want, you can verify by calculation by putting in half a period, because 10 is half a period. 5, this was a quarter of a period. This is half of a period. 3/4, this is 1 period. So we have 2 cycles in here. Use your line in A Roman 2 to explain why the mean power dissipated in the resistor is 23 milliwatts. Let's just look at the graph. So if we look at the graph, this is 46. We notice that the mean is the average, and we notice that the graph is going to be symmetrical at around 46 divided by 2, that is 23, I think. So at around 23, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is around here. So the graph is symmetrical, or the line is symmetrical at about 46 milliwatts divided by 2. The line is symmetrical at about 46 milliwatts divided by 2, which is approximately 23 milliwatts. Hence, the mean power is equal to 23 milliwatts. If the graph was symmetric about the x-axis, then we would say the mean power is 0. But of course, for power, it is always above the x-axis. So the mean power is 23 because the line is symmetrical at about 46 divided by 2. Then the alternating voltage in A is now applied to a piezoelectric crystal. Of course, we know here this is production of ultrasound. And remember, the frequency was, what was the frequency? Was 50 kilohertz. The frequency was 50 kilohertz, which is already greater than 20 kilohertz. So that means the frequency is already in the ultrasound frequency range. Explain what happens to the air surrounding the crystal. So the alternating PD is going to make the crystal to vibrate. Because it's alternating, the alternating PD makes the crystal to vibrate. And what does the vibrating crystal do? The vibration of the crystal is also going to cause the air around the crystal to vibrate. So the vibration of the crystal causes the air around to vibrate. Since there are 3 marks, I will talk about the frequency. The frequency of vibration the frequency of vibration. Sorry, the frequency of vibration is in the ultrasound frequency range, or is in the ultrasound range. That is, it is greater than 20 kilohertz. So the frequency, well, remember the frequency of the applied PD was 50 kilohertz. So the frequency of vibration of the crystal is in the ultrasound frequency range. Okay. So the alternating PD is going to make the crystal to vibrate, and the vibration of the crystal is going to cause the air molecules around the crystal to vibrate. And the frequency of vibration is going to be in the ultrasound range. Then a second piezoelectric crystal is placed in the air near to the first crystal. Explain the effect of the surrounding air in B on the second crystal. So it means, remember this, the surrounding air is already vibrating. So the air is going to again make the second crystal to vibrate. So the air makes the second crystal to vibrate. Of course, if the second crystal vibrates, it is going to create an EMF, so which generates or which causes an EMF to be generated across the second crystal, which causes an EMF to be generated across the second crystal. Because the air is already vibrating, it means any crystal placed around that air will also be forced to vibrate. And if a crystal vibrates, then a PD is created across the crystal, which results into an EMF across the second crystal. That is ultrasound. Question 8 is quantum physics, I think. Said what is meant by work function, energy of a metal. Well, the word work function is the minimum energy of electromagnetic radiation the minimum energy of electromagnetic radiation required to remove an electron from a metal surface. That minimum energy of electromagnetic radiation which is needed to remove an electron from a metal surface is what we call work function. Now you should be referring to the minimum because it's the smallest, and you should be referring to either photons or electromagnetic radiation for you to get these 2 marks. Ultraviolet radiation of frequency 1.36 times 10 to the power of 15 Hz is incident in a vacuum on a metal surface. The power of the radiation incident on the metal surface is 8.36 milliwatts. Photoelectrons are emitted with a maximum kinetic energy of 3.09 times 10 to the power of minus 19 joules. Determine the number of photons incident on the surface per unit time. So let's first find energy of each photon. Energy of each photon. Of course, the energy of each photon is given by h times f. We have the frequency, we know what h is. So it means the number of photons is going to be the total energy divided by hf. Total energy was the power of the radiation incident on the surface is 8.36 milliwatts. Photoelectrons are emitted with a maximum kinetic energy of 3.09 times 10 to the power of negative 19 joules. Determine the number of photons incident on the surface per unit time. So the total energy is going to be power over time. So we want the number of photons per unit time. So it means total energy, time is going to be 1 second because it's per unit time. So total energy is going to be 8 point, because power is energy over time, energy is power. This is power times time, not power over time. Energy is going to be power times time. So this is going to be 8.36 times 10 to the power of minus 3, then times time, which is 1 second. So total energy is going to be 8.36 times 10 to the power of minus 3 divided by h, which is 6.63 times 10 to the power of minus 34. Then times f, which is 1.36 times 10 to the power of 15. So I'll check with my calculator. 8.36 exponent minus 3 divided by, open brackets, 6.63 exponent minus 34 divided by 1.36 exponent 15. So I'm finding the number of this to be 9.27 times 10 to the power of 15. Yes. Then calculate the work function energy phi of the metal. Remember, the photon energy hf is equal to the work function phi plus the maximum kinetic energy Emax. That is called Einstein's equation of photoelectric effect. So the work function phi is equal to the photon energy, which is hf minus Emax. So I'll just substitute the photon energy. Remember, the photon energy was 6.63 times 10 to the power of minus 34 times 1.36 times 10 to the power of 15. Then minus the maximum energy was 3.09 times 10 to the power of minus 19. So I'll check my calculator. 6.63 exponent minus 34 times 1.36 exponent 15, then minus 3.09 exponent minus 19. So I'm getting 5.93 times 10 to the power of minus 19. So that would be the work function. The frequency of the radiation incident on the surface in B is increased. So they are increasing frequency while the power is constant. Remember, intensity is equal to power per unit area, which is going to be equal to they say the frequency is increased. So this is going to be H, or it is energy over time, then times A. Remember, energy is HF, then over T times A, times the number of photons, of course, times the number of photons. So it means the intensity is going to be equal to N HF. This is over T over area. Okay, so state and explain the effect of this change on the maximum kinetic energy. Of course, for maximum kinetic energy, HF is equal to phi plus Emax. So if the frequency has been increased, work function is a constant. It means the maximum kinetic energy must, of course, increase, because the maximum kinetic energy is HF minus phi. So if F is increased, the maximum kinetic energy must increase. So I would say greater photon energy. There's greater photon energy for the same work function, because work function depends on the metal. If it's the same metal, it is the same work function. For the same work function, so the maximum kinetic energy is increased. So the maximum kinetic energy is increased. Okay, then the second one is the rate, which is N over T. So N over T, when we say the power is constant, it means the intensity is constant. So N over T is equal to intensity, which is constant, times the cross-sectional area, or divided by HF over A, when I make N over T the subject. So A is the constant, area is a constant, intensity is a constant, H is a constant, so it means N over T is inversely proportional to F. If we increase F, it means the rate is going to be smaller. So the rate of emission of photoelectrons. So greater photon energy at the same power means a lower number of photons incident on the surface per unit time. So greater photon energy and same power is the same as saying same intensity. Same power means lower number of photons. Lower number of photons per unit time incident on the surface. And remember, the rate of emission of photoelectrons depends on the number of photons incident on the surface. Since each photon or each electron, since each electron absorbs one photon, the rate of emission is low. So N over T is going to decrease, because N over T is the number of photons incident on the surface per unit time, which is directly proportional to the number of electrons which leave the surface. So since every electron just absorbs one photon, it means the rate of emission is going to be low, because there are fewer photons incident on the surface per unit time. Okay. Question 9 is Astrophysics and Cosmology. State what is meant by the luminosity of the star. So we know that luminosity is the total radiant power emitted by the star. Total radiant power. Total radiant power emitted by the star. Then a star in the constellation Canis Major is a distance 8.14 times 10 to the power of 16 meters. Remember, a constellation is a group of stars which form a certain pattern in the night sky. So it is a distance of 8.14 times 10 to the power of 16 meters from the Earth and has a luminosity of, so this is distance, this is luminosity, 9.86 times 10 to the power of 27 watts. The surface temperature of the star is 9830 Kelvin. Calculate the radiant flux intensity, that is F, of the radiation from the star observed from the Earth. Give a unit with your answer. So we know that radiant flux intensity is L divided by 4 pi times d squared. The luminosity is given as 9.86 times 10 to the power of 27 divided by 4 pi, and the distance is 8.14 times 10 to the power of 16, but this should be squared. Of course, this is radiant flux intensity, so the units are going to be, this is meters squared, the other one is watts, so it is watts per meter squared, watts per meter squared. Because luminosity is in watts, the distance squared is in meters squared, so it is watts per meter squared. So just check with my calculator. Let me start with the denominator, 4 pi times 8.14 exponent 16 squared. Then I have 9.86 exponent 27 divided by the answer. So this is 1.18 times 10 to the power of minus 7. Then determine the radius of the star. Determine the radius of the star. So of course I will go to luminosity equals to 4 pi times sigma times r squared t power 4. These equations are given in the list of formula. So the luminosity has been given as 9.86 times 10 to the power of, I think it is 27. This should be equal to 4 pi. Stefan Boltzmann's constant is given as 5.67 times 10 to the power of minus 8. You can check in the list of constants. Then times the radius squared. Then times the temperature was 9830. So it's 9830 raised to power 4. So I'm just going to divide with my calculator. So I'll start by dividing this by 9.86 exponent 27 divide by, let me start with the simplest, 4 pi divide by, I'll divide by 5.67 exponent minus 8. I'll again divide by the temperature, which is 9830 power. I'll have to change the power to power 4. Then I'll have to find the square root. So this is 1.22 times 10 to the power of 369. So R is 1.22 times 10 to the power of 9. 1.22 times 10 to the power of 9 in meters. Explain how the surface temperature of a distant star may be determined from the wavelength spectrum of the light from the star. Remember, by Wien's displacement law, lambda max times T is equal to constant. So it's like we must tell the wavelength of the distant star by looking at its spectrum. Then we must also find the wavelength of a star whose surface temperature is known. Then we use this equation to be able to find the unknown temperature. So I'll simply say wavelength at which peak intensity occurs is determined from the spectrum of the star. The wavelength at which peak or maximum intensity occurs is determined from or by looking at the spectrum of the star. From the spectrum of the star. Then we should also find the wavelength at which peak intensity occurs for an object or for a galaxy of known temperature or for any star of known temperature, which is going to be called the standard candle. So the wavelength at which peak intensity occurs for an object of known temperature is also determined. Imagine you have lambda 1 T equals to lambda 2. This is T1, lambda T2. So let's say this one, its temperature is known, which we find its wavelength. So we know those two. This one, its wavelength is known, but we don't know its temperature. So we use this equation here to find T2. So the wavelength at which peak intensity occurs for an object of known temperature is also determined. So by Wien's displacement law, the wavelength at which peak intensity occurs is inversely proportional to the temperature. By Wien's displacement law, wavelength at which peak intensity occurs is inversely proportional to the absolute temperature. In other words, I'm saying lambda max times T equals to a constant. So from three equations, if I equate them, I have the wavelength of a known temperature, and I have the wavelength of the unknown temperature, so I can find the unknown temperature by Wien's displacement law. Okay. The last question, I think this is nuclear physics. State what is meant by random. Of course, random means it cannot predict which nucleus in a given sample will decay next. Cannot predict which nucleus in a given sample will decay next. Then spontaneous means not affected by external factors. Spontaneous means not affected by external factors. External factors such as temperature, pressure, catalysts, etc. So something spontaneous is not affected by the environment. So that is the meaning of spontaneous and random. A small sample of carbon-15 decays. The mass m of carbon-15 in the sample decreases with time as shown in the figure. The figure shows the variation with the t of the value of ln of m. Okay. State how the figure demonstrates that radioactive decay is random. You see that it's not a straight line. So the line fluctuates, or the trend is not a straight line. So you can say the line fluctuates. Or you can simply say the trend is not a straight line. So because the trend is not a perfect straight line, then the radioactivity is random. We cannot predict which nucleus in a given sample will decay next. Then on the figure, draw a straight line of best fit. So I'll just draw a line through this trend, through this fluctuating trend. So I will try to draw a straight line through this trend. Just put a ruler along this trend and draw a straight line through it. Okay, I've tried my level best. You can draw a better line. Then show that the decay constant lambda of carbon-15 is given by the magnitude of the gradient. Of course, this is mathematics. We have a graph of ln of m against t. It is against time t in seconds. Okay. So in general, we know that x equals to x naught e power negative lambda t. So I'll say m equals to m naught exponent power negative lambda times t. If I introduce natural logarithm, so I'll have ln of m equals to ln of m naught plus negative lambda times t. So if I rearrange this, ln of m is equal to negative lambda times t plus ln of m naught. So if I compare with y equals to mx plus, that is the equation of a straight line. So you notice that the gradient is equal to negative lambda. So the gradient is equal to negative lambda, which means that the magnitude of the gradient is lambda. So the mathematics here just carries 1 mark. So use your answer in B Roman 2, which is the grade. B Roman 2, what is B Roman 2? Was the straight line. To determine lambda, give a unit with your answer. So we say the gradient. Remember, the gradient is equal to negative lambda, so I just need to find the gradient. So I'll choose 2 values from this straight line. And my line is stopping here at this point here, so I'll take this as my last point. I'll take off 2 small squares, this point here, which is 11, 10.1, 2, 3, 4. Okay, this is 11, 11.2, 11.4, 11.6. That is 11.6. And I will take this point here also, which is this is negative 5, negative 4 point. I think that is negative 4.8. Okay, so negative 4.8 and negative 8. So this is going to be equal to the negative of negative 8.0 minus or let me do it the other way around. This is the first point, this is the other one is the last point. So I'll start from the last point. The first point is, or the last point is negative 8 minus negative 8 minus negative 4.8. Negative 8 minus negative 4.8 divide by negative 8 was corresponding to 11.6 minus this corresponds to 0. This is minus 0. Okay, I hope I did this correctly. Let me see, negative 8. No, it is the other way around. 4.8 corresponds to 0. Negative 4. Okay, that is fine. So I have that negative lambda is equal to, I'll just press my calculator. I have negative 8 plus negative 8 plus 4.8. The gradient is negative lambda. Okay, so this is going to be that divided by 11.6. This minus here is not necessary because the gradient is negative lambda, so I don't need to put a negative on the gradient because the gradient itself is going to be negative. So this gives me negative that one, negative 16 divided by 59. So what is lambda? Lambda is going to be positive, so the answer here is 0.27. It is 0.27. Okay, I'll have to check this again. The scale on the vertical is 0.2. So this is 4.6, not 4.8. Sorry. This is negative 4.6, 4.2, 4.6, 4.85. What is the scale here? 1 divided by, so it's 0.1. 1, 2, 3, 4, 5, 6, 7. It is 4.8. That's negative 4.8. So you have negative 8 plus 4.8 divided by 11.6. Yeah, it's negative. It's negative. This is not correct. I pressed my calculator wrongly. So negative 8 plus 4.8 divided by 11.6. So this is negative 8 over 29, which is the same as negative 0.28. So this is 28. Of course, the units of decay constant is automatically per second. Use your answer to calculate the half-life of carbon 15. So we know that decay constant lambda is equal to ln of 2 over T1/2. So the half-life is going to be ln of 2 over the decay constant, which is going to be ln of 2 divided by 0.28. Ln of 2 divided by 0.28. So this is 2.5. So the half-life is 2.5. Then the equation for the decay of carbon 15 can be written as, so this is the decay equation. State and explain how the mass of the products of the decay must compare with the mass of the carbon-15 nucleus. So if this reaction is to occur, then there should be a difference in mass. And if energy is to be released, then it means for energy to be released in any reaction, it means the mass on the right hand side should be less than the mass on the left hand side, so that energy is released in compensation for the difference in mass. So I will say for the reaction to occur, energy must be released. Energy must be released. Where does this energy come from? So I will say energy release comes from the difference in mass. So it comes from the difference in mass on both sides of the equation. So the total mass, so it means the total mass of the products must be less than the mass of the carbon-15. So the total mass of these products on the right hand side must be less than the mass of carbon-15, so that energy is released to compensate for the difference in mass. So for this reaction to occur, energy is going to be released. Why? This energy should come from the difference in mass on both sides of the equation, which means total mass on the right hand side should be less than the mass of the products. By Albert Einstein's mass energy relation, um, energy is going to be released to compensate for the difference in mass on the other side of the equation. So energy is going to be released. I think that marks the end of this paper. I took much more time, but I tried my level best to explain the concepts. Until next time, bye bye.